In the last lesson, we learned about series circuits. Today, we're going to focus mostly on parallel. So we saw a series circuit was where you had one path, and if you disrupted the flow of current at any point, such as taking out a light bulb, having the light bulb burn out, putting a switch or a fuse, it shuts off the entire circuit. We saw that a parallel circuit was made up of multiple paths for the electrons to follow, and we saw that each path was independent of all the others. So disrupting the flow in the middle path had no effect on the other paths. We saw with the series circuit again, switches would shut off the entire path regardless of where you put the switch. We saw that series circuits were beautiful when you wanted one component to have an effect on the other. We wanted our resistor to limit the amount of electricity getting to the speaker. They need to be in series. It won't work otherwise. We saw the same thing with the hair dryer, and when we were talking about the wire bringing the electricity into the hair dryer. As a summary from the last lesson on series circuits, make sure you have all of these points. Series circuits, one path, a break shuts down the entire circuit. Switches and fuses should always be in series with what they're protecting or controlling. A resistor should always be in series with the thing it's limiting the current to. All parts of a series circuit get the same current since there's only one path. The voltage of each part adds separately to the voltage of your power source. And the component with the highest resistance will get the most voltage. Today we want to focus on parallel. So again, parallel, multiple paths. Each path is independent of all the other paths. Here we have some switches in a parallel circuit, and if we were to throw switch 2, it would shut off just that one bulb. If we throw switch 3, it shuts off only that bulb. Note, it is possible to put a switch where I did for switch 1 that would shut off both of the bulbs. So depending on the placement determines if the switch shuts down the whole circuit or just one branch of the parallel. Where do we use parallel? Well, one of the places is like in your kitchen lights. If you have more than a single light, each of these lights is connected in parallel with the others. If one of these bulbs burns out, the others keep shining. They're independent of each other. It's not like a Christmas tree string where one bulb burning out shuts down the whole strand of lights. Each strand gets the full voltage. Okay, so it may look something like this. 4 light bulbs, 1, 2, 3, 4, all in parallel. You'll notice there's a switch here that is not part of any individual branch, but will shut all 4 of them down at once. Alternatively, you might put the switches where I have them in this picture. This switch may shut off 2 of the lights. This switch would shut off the other 2 lights. So depending on the functionality determines how you want to wire up your circuit. Okay, here is a kitchen light, much like the one that I have in my home, where it has a spot for 4 bulbs, and it's a hodgepodge of different resistances. I never have all the bulbs matched because when one burns out, I replace it by whatever's available. It becomes a Frankenstein monster of a chandelier. So I'd like you to figure out what is the power of each of these separate bulbs. How much current is going through each of these separate bulbs. So pause it, draw it, and then we'll work through this together. Okay, the first important thing to realize is in parallel they are all connected directly to the power source. That means every single one of these gets 120 volts. The standard voltage for an American outlet. Okay, once you have the voltage, you could then find for each one of them how much current flows through it. So I'm going to do a couple for you. You can do them all. I will do the current through this branch. 120 volts, 240 ohms. I divide and I get half an amp. This bottom one, 120 volts, 120 ohms, that gives me 1 amp. Again, you could do the same thing, and you should do the same thing for these other two. Find out how much current flows through each path. You'll notice that more current flows when there is less resistance. So this branch should have the greatest amount of current. Okay? Once you've got all your current, you can then find the power, which will help determine the brightness of the bulb. So we take the voltage, which is 120 for all branches, and multiply by the current. So for this first one I did, we get 60 watts. That light bulb is a 60 watt bulb. I then do it for this one, 120 times 1 amp, and I get 120 watts. That light bulb would be the brighter of the two lights. Again, do the same thing to find the power of those two bulbs. You should find, again, the one with the most resistance gets the least power. This is opposite from a series circuit where the one with the most resistance got the most voltage. Now they all get the same voltage, so the easier path gets more current. Okay, here's one where I worked out all the details ahead of time, and what I'd like you to focus on is not all the preliminary stuff that we just did together, but I'd like you to take a look at this number right here. This is the current that came out of the battery. This is the total current. And you get the total current by adding together all of the individual currents that you calculated. So when you calculate your currents by doing volts over resistance, and you get all your answers, you add path 1, path 2, path 3, and that will tell you how much current came out of your power source. Now the reason why that's important is because many times these power sources will have a fuse. And the fuse will blow if we exceed the total current allowed to go through that fuse. Okay? So one more time. Calculate all your individual currents, add up the current for each path, and make sure it does not exceed the value of your fuse. So here's a fuse box on a car, and you can see there's lots of different numbers here. We have a 10 amp fuse, we have a 15 amp fuse, a 30 amp fuse, we have a 7.5 amp fuse. So different fuses to protect different parts of your car's electrical system. You want to make sure that you do not exceed the value of your current that's stamped on that fuse. If you do, the fuse blows out. It's in there to protect your expensive electronic equipment in your car. Okay, so the fuse blows instead of destroying your radio or your wiper motor or whatever else it might be protecting. So here's one you could try on your own. See if you can find the total current coming out of this battery. Okay, start out. Give every branch the same voltage. Use the voltage to find the current in all three branches, and then simply add them all together. Okay, I want to make sure you know if we are trying to find total resistance, when they're in series, you simply add the two numbers together. That would give me a total of 70 ohms. If you have three, you just add them all together. It's in series, so the electricity has to go through all three of them. That would give me a total of 60 ohms. Here's where it gets a little tricky. If you are in parallel, adding more resistors actually makes it easier because you've given the electricity another option where it can flow. So in this case, this would not give you a total of 40. The way you get your total resistance in a parallel is you add the inverses of all of your different resistors together. So we'd have 1 over 20 plus 1 over 20. Remember how to add fractions? That's not 1 over 40. That's 2 over 20. We make sure we have a common denominator and we add the tops, not the bottoms. We could then invert both of these, or we could cross multiply. Either way, we get a total resistance of 10 ohms. Notice the resistance got less. That should always happen. In a parallel circuit, you have less resistance because you've made it easier by having extra paths. If we had 4 resistors, we would do 1 over 20 4 times. That would be 4 over 20. Then when we cross multiply and do our math, we get a total resistance of 5. Notice that if all the resistors are the same, a shortcut is just divide by the number of resistors. So 20 divided by 2 was 10. 20 divided by 4 gave us 5. This trick only works if all the resistors are the same. If not, you must add the reciprocals. So that is how we deal with parallel circuits. Parallel circuits, again, have more than one path. The most current follows the easiest path, the one with the least resistance. You add up all of your currents to get your total, and they all get full voltage. All right, so that is parallel circuits in a nutshell.